Hello everyone, my name is Steve Pratt, Marketing Director at SciTime, and my guest today is Hassan Tabatsbeh, Applications Engineering Director. He's going to kick off a three-part series about Jitter. Welcome, Hassan.
Thank you, Steve.
Hey, I'm really glad that you're breaking up this discussion about Jitter into three parts. I mean, Jitter is such a complicated topic and has many components to it. Can you start by defining Jitter and the types of applications that care about Jitter?
Sure. Let me move to the next slide. Jitter is a time domain parameter. It's defined as deviation of some event timing relative to ideal value. The event can be is defined depending on type of jitter. It can be an edge, can be the time interval between two edges or three edges, or it can be defining the edge locations over time. The ideal values typically are defined based on some assumption of ideal clock. In practice, it's usually some sort of average value extracted from the edges measured. There are many jitter definitions. The most important ones are the ones listed here. Period jitter, which is deviation of a clock period or a single cycle interval from the average value. That is the one that we're focusing today. And there are also other types of jitter often used, cycle to cycle. Long-term jitter, which is jitter over a large number of cycles, and time interval jitter or phase jitter, which is typically used in serial interface jitter budget estimation.
All right, there's lots of types of jitter, and because of these 15-minute duration for the webinar, you're going to focus on period jitter today?
Yes. I specifically chose to focus on period jitter, not because it's the most important one, but because it's the most intuitive one, and it makes it easy to explain the measurement issues that typically customers run into.
Very good.
Let's move on to the next slide. Who cares about clock jitter? Typically, digital applications that work in time domain care about jitter. Those type of applications include computers like a processor, CPUs, and microcontrollers, data servers, network interface cards, telecom equipment, embedded systems, graphic and video, and you can see that one of the common themes in this type of application is some sort of a processor engine. Consumer electronics like cameras and game consoles. What typically is not defined in terms of jitter are RF applications and GPS applications. Those type of applications care about phase in the frequency domain as opposed to time domain. Therefore, jitter is typically not used for performance evaluation of this type of applications. Let's move on to period jitter. Let's define period jitter. Period jitter is defined as variation of cycles of a signal over time relative to some average value. So in this plot, you can see that T1 and T2 and T3, these are different cycles of the clock signal measured up to Tk. Each one of those is called a hit. Each one of those cycles is called a hit. So we can, for example, measure 10,000 hit of period. In the old times, the way it was measured was to basically trigger at one edge and look at the deviation or movements of the second edge related to first edge. And that was a very intuitive way of looking at the jitter, not necessarily the best way to measure jitter, but very intuitive way. Today with digital oscilloscopes, this is hardly used. We don't also recommend using that method. At the bottom of the screen, you can see the mathematical formula representing jitter. So period jitter samples is measured by subtracting the actual value of the interval measured from the average value, T of C. And typically it's expressed as RMS value, which would be standard deviation of those periods measured. That is basically the power in deviations of those signals, the RMS power, which gives us RMS jitter. Here I'm showing a system that includes a number of blocks, CPUs and memory and peripheral devices. Each one of those have sort of an interface to talk to each other. And those interfaces are either serial, like PCI Express and SATA, or parallel, like the DDRs and PCI. Any of those interfaces and engines have their own clocks typically, and period jitter impacts many of those blocks, like the CPUs, because of the critical timing in those engines, period jitter becomes important, also in parallel interfaces. In terms of performance limits, here I have a table which has more information that is needed for this talk. But a clock that typically is used for processor engines, state machines I call them as a class of circuits, require this type of performances in terms of frequency ranges and so on. I'm going to focus on period jitter. The period jitter, which is the third line of the table. The requirement for most applications are 4 picosecond RMS to 100 picosecond RMS. And Cytan has parts today that easily do 1 picosecond RMS up to 5 picosecond jitter. Cycle jitter, which we're not focusing today, it's also important for some of the peripheral devices like DDR, memory devices. And requirements are around 20 to 500 picosecond, and Cytan parts do support 8 to 50 picosecond, easily meet cycle jitter requirement for this type of applications.
All right, so thanks for the that description of the applications that are concerned about period jitter. Now, can you help us understand some of the test setup and measurement error sources and solutions when testing for period jitter?
Sure. That's in fact one of the main reasons I decided to focus on period jitter, because I wanted to explain jitter measurement methodologies. That is one of the most commonly asked questions and issues that our customers run into: how to do good jitter measurement, how to reproduce numbers we have on our data sheet. So that's the focus of this section. Most people use today real-time oscilloscopes for jitter measurement, and that's what we're going to focus on. There are many other methods to measure jitter, especially period jitter, like equivalent time scopes, time interval analyzers, bit rate testers, and so on. But I don't focus on those today because they are not commonly used anymore, since real-time scopes are so powerful today.
Great. So we're focusing on real-time sampling scopes.
Yes, those are we are focusing on. To explain how to do a good measurement, let me spend a minute to describe how scope does jitter measurement. So scope is a sampler, effectively. So it takes the signal as a voltage signal, and it tries to measure the voltages and represent them with digital numbers at different times. Here on the screen, I'm showing the cycle of a signal, a clock signal, that is being sampled at some uniform intervals. The scope is going to try to reproduce numbers that closely match the voltages measured. But always there is some level of error associated with that, related to internal circuits or just limited resolution of the analog to digital converter in the scope. Typically those are around 8 to 10 bits. Once the samples are ready, the scope has to estimate at what point in time the signal edge, either rising or falling, crosses a 50% threshold. There may not be any voltage sample at that point in time. Therefore, the scope does what is called interpolation. It uses the points it has, interpolates them, and then it estimates at what time the signal crossed 50% threshold. And that's really the principle that the scopes use to estimate time edge, and from there, the differences of those become period jitter.
But because it's sampling and interpolating, it could also cause error sources.
Exactly. So the sampling mechanism interpolation causes certain error sources, which are very important to understand to be able to do very good jitter measurement. Let's move on to the next slide. A real-time scope inside the channel has two main components. One is an amplifier that basically amplifies the signal or attenuates it. That is done. That is basically the way scope responds to the vertical knob on the scope. And then it has an ADC, analog to digital converter, that samples that signal. Each one of those components has a certain amount of noise associated with it. The amplifier has certain noise inside it. And that noise, how much of it shows up at its output, depends on the slew rate of the signal at the input of the amplifier. So two things impact its noise performance. The ADC has a quantization noise because it cannot reproduce the signal infinitely with infinite precision. There's a time base that is used to clock the ADC, and that time base has its own jitter. This is one of the critical specs of any scope you buy, so very important to pay attention to that. There's also a sampling rate associated with that needs to be high. And a trigger jitter. Trigger jitter, I'm not going to discuss it because in most today's scope, if you do it right, trigger jitter typically is not a dominant source. All these sources cause two types of jitters. One is what is called voltage noise converted to jitter, or voltage to jitter conversion. For example, the amplifier noise is a voltage level noise, but it does show up as jitter. And the other type is a timing jitter. Basically, those samples that are used to clock the ADC, if they are not right on where they should be, it causes a certain amount of additional jitter measured. And in terms of math, basically the jitter of the signal, JSUT, which is the signal, a couple of other components get added to it, which are now scope-related, time-based jitter and voltage to jitter conversion jitter. So what is in the signal and what is measured are different because of the scope contribution. The objective is to reduce the effect of the scope contributions and at least know what the limits or no's are.
All right, so tell us how we can reduce some of these error sources.
Sure. Let's look at voltage to jitter conversion first. If you have a signal which has a certain slew rate, basically a certain rise time to it, and there's a voltage noise, which is shown basically on the left side of the screen, that voltage noise translates into a time noise through the slope of that edge. This is called voltage to jitter conversion. If the slew rate of the signal is faster, for the same amount of voltage noise, you get a lot less.
Yeah, makes sense. Yeah.
Timing jitter. Effectively, the edge is much more defined because it's much faster.
Yeah. Okay.
Now, to reduce the effect of scope noise, there are two things that can be done. One is to sharpen the edge, basically increase the slew rate of the signal. Also reduce the noise of the scope. Basically, the two components that are shown in the plot needs to be optimized. Let's see the effect. Here we have an example. Typically, we recommend setting the scope bandwidth to somewhere around 1 over the 2080 rise time of the signal. So if the rise time of ultimate signal is 1 nanosecond, you would want to set up the scope at around 1 gigahertz, because at that point you can see the edge without much impact from the scope, but you minimize the effect of the noise of the input amplifier. The higher the bandwidth of that amplifier is, the more noise goes through it. So you don't want to have too much bandwidth in an amplifier if you don't need it.
So, Sasan, is there a rule of thumb then to help with the scope bandwidth setting?
Yes. Here's an example. 1 over 2080, 20% to 80% rise time or fall time of the signal. That's a rule of thumb. For a 1 nanosecond rise time fall time, you would go for 1 gigahertz.
Okay.
Here at the bottom of the screen, I'm showing two examples here. One with, on the left side of the screen, we set the scope to 8 gigahertz. And on the right side, we set the scope to 2 gigahertz. And you can see with the wider bandwidth, we measure 3.5 picosecond. And with narrower bandwidth, we
Cut
measure
the jitter in half,
1.7.
just by the scope bandwidth.
So very important point.
Very cool.
There's another factor that impacts the jitter, voltage to jitter conversion, that's sampling rate. Here we're showing two examples. One, we set the scope to 5 picosamples per second. This is the Agilent scope, which can support 40, but for demonstration purposes, we set it to 5 picosamples per second. And we measure 2.1 picosecond RMS. And the other one is 40 picosamples per second, and we measured 0.9. So clearly sampling rate has impact on measurement accuracy.
Yep.
Let's move on to the other important parameter, which is slew rate. Most scopes for doing analysis on the signals recommend putting the full signal on the screen. In other words, you can see
right.
the full signal swing on the screen. Jitter is one of the cases where you don't want to do that. because if you do that, the slew rate on the scope effectively is slower. And that slower slew rate causes the quantization noise to show up in jitter measurement. By decreasing the voltage vertical division, you can increase the slew rate of the signal and reduce the jitter impact of those quantization noises.
Cool. Okay. So now we know more about the real-time scope's error sources from the voltage noise to jitter conversion, and such as decreasing the scope's noise through the bandwidth, matching the scope's bandwidth with the signal, increasing the sampling rate, as what you're showing here, choosing a smaller vertical setting, such as 50 millivolts per division for LV-CMOS. Cool. Okay. Can you tell us about the error that can come from a scope's time base now?
Yeah, so the scope time base is something that is very difficult to reduce. It is characteristic of the scope. You have to know how it impacts your measurement. So here at the bottom of the screen, bottom portion of the screen, we are showing how much error in measurement results from certain time-based jitter error for a given jitter in the signal. For example, at 1 picosecond RMS jitter in the signal, the accuracy could be better than 5% if the scope jitter is less than quarter picosecond. But if the scope jitter is also 1 picosecond, then the error would be around 40%.